So as I said, I mean, we are going to solve a major problem. The problem is this, that if you have got an outcome variable or an example where you will be analyzing a data set which has got three variables. To give you an example, let's say you are interested to study the length of stay at a hospital, and you have made measurements on particular dosage of a drug that is given in the inpatient's department and the age of a patient, right? Age of patients. You would like to investigate whether the length of stay in the hospital ward is any way related to the dosage of the drug given to these patients, and whether age could be a factor that could influence this association. This is a very simplistic, almost like an artificial scenario that we have drawn here. But if this were something that you'd be interested in, then the analysis of your choice would be a multiple linear regression. Because let's say that you assume that there is a linear relationship between the drug dosage and the length of stay in the hospital. So then that would be how you would look at it. In this set of lecture, we are going to introduce some of the concepts of multiple linear regression, again, keeping in context that we are dealing with a particular software programming environment, which is R. So we're going to confine ourselves to those because this is a rather complicated topic. It involves quite a few concepts. We won't be able to touch all of these things, all of them, but we'll try. And then we'll learn that we can examine some assumptions and we'll do some diagnostics. Because one of the things that you may have already picked up in this course is this, that in general, when we use R for any kind of data analytical work, the first thing is this, that we do some sort of a graphical examination, then we run some procedures, and then we run some diagnostics, and that's how we try to make sense of the association between the various variables that we deal in this course. And we should also learn how we can fit models in multiple linear regressions. So let us get to some preliminaries and some preliminary ideas that we'd like to discuss here. And one of the things that I usually do in discussing the preliminaries in this course, as you may have seen, is this, that we introduce the data sets here. But because this is an artificial situation and we are trying to understand the core principles of data analysis using R, we may take several data sets and we can take bits and pieces. And I just wanted to introduce you to the data set that we're going to use now. And one of the ideas that I wanted to do was that I wanted to start analysis of some data on the crime rates in the United States, but I found that there could be some better data sets. For example, there are data sets in the Julian Faraway's package, which you've been using for a while. The Faraway package, and they had data sets such as Gala and Pima. You can load those data sets and work alongside with me. You don't necessarily have to use the data set that I am using, although you can. So learn from what I'm doing, but use it to your own data sets. There are plenty of data sets in the world around, and you can just pick up that next. So what I'm going to do is I'm going to introduce you to the data set that I'm going to use so that it may make some sense. The dataset that I'm using for this paper, for this work, is the dataset on the concentrations of creatine phosphokinase, which is like a muscle protein, and on age and weight. So it could be like explaining whether body weight can better explain creatine phosphokinase in urine, or whether that is a factor that should be considered when we consider age as well. Or maybe we say that, okay, what happens as people grow older? Do creatine phosphokinase levels fall off, or they tend to increase? And does it mean that people who are heavier, or after adjusting for their weight, what happens to that? So, and the other thing, of course, is this, that on the right-hand side, you can see that we have put together the summary and the tables, etc., etc. So Let's further conceptualize this model a little bit. Now, if you have the data set, that is, if you have the blood CPK data set which is included in this package, you can run with this, but if you don't, you can use your own data set. But remember that you pick up 3 variables. All the 3 variables must be continuous variables. And you fix as one variable as your outcome variable, whose variability you would like to explain, and keep the other 2 variables as your explanatory variables and covariates. Do it in a manner that makes sense to you, because without context, a multiple linear regression will not much make sense to anyone, least of all to you yourself. You can use RStudio, and in the R coding window, you can write the following codes. So let me go over this slowly to make sense of what we have done. So take up the first line, CPK, then there's a tilde, and then there is a B0 plus B1 times age plus B2 times weight. Let's make some sense of this. CPK in our context is creatine phosphokinase. B0, the tilde mark is, as you know, it's according to Wilkinson-Rogers formula. This is the mark that we put to to specify that there is a linear model that's coming. B0 actually stands for what is known as beta 0, or the intercept. B1 stands for the slope parameter for the variable age. This B1. So we have B1 times age. Now, this is the thing. While B1 times age actually is quite literally can be interpreted as a product term for B1 and age, in general, its interpretation is a little bit more complex. It's not exactly a multiple term. It is like B1 of age. So the interpretation is this, that as B1, as age increases by 1 unit, B1 remains constant. What will be the increment in CPK after controlling for weight and taking into consideration the intercept term? Then we add a plus sign. Now this plus sign is not a literal addition. In other words, you do not really add anything to get CPK. These are just there as an additional variable that we put in. And in this particular case, that additional variable is a variable of weight. That variable of weight has got a regression coefficient, and that regression coefficient is beta 2 or B2, as you can see here. So we say in the end that creatine phosphokinase can be explained by or predicted by a combination of age and weight. Now, coming back to the R speak, or the language conventions of R, we can put in a Wilkinson-Rogers formula in here, which goes like cpk.lm, which is the object to which we store the product of the linear model, if you will, of CPK, which is the outcome variable, therefore it sits to the leftmost end. Then we initiate that with a tilde mark. We add the age plus weight. Remember that plus sign does not mean age and weight are added together. So age and weight. Then we specify the data. And then we order that we want a summary of that particular object, which is cpk.lm, which is stored in another object called sum_cpk. That's as simple as that. So let's see if we get the sum_cpk. So print out sum_cpk. What do we get out of that? That's the output from the regression model. And when we do this, we get to see the residuals. And you can see that these residuals, which is the residual of the composite model, do not exactly follow a normal distribution or Gaussian distribution. In other words, age and weight would have to be composite normal. In other words, the two variables in a three-dimensional space would give you sort of a hill which looks like a normally distributed on all sides that you want to look at it. Well, certainly, I mean, the residuals do not tell us that, so there's something that we need to do about it. In the second part of this output, we get to see the beta coefficient. So for the intercept term that we have included the intercept term here, we could not have, or we may not have included intercept term here as well. And you can see that the intercept term is very big, minus 932. And then you can see that the t-values and the p-value for this, t-statistic and the p-value for this term, and you can see that the p-value is non-significant at 0.05 levels. So you could, in theory, remove the intercept term because it's not going to add any more new information than what you've already got here. Then we've got the age in years, and you can see that the age in years is marginally significant at 0.05, and you can see that there is an effect of -7. So as age increases, the CPK level comes down, is what it would suggest. And you see that the weight has got a bigger component to it, although we don't know whether weight is any bigger than weight's contribution is bigger than that. But what we know is this, that as weight increases per kg of the weight, there will be a corresponding increase in the CPK concentration in urine. The model itself is statistically significant at 0.5 level, and you know that the adjusted R-square is around 40% with this configuration, stating that about 40% roughly can be explained by invoking these two variables alone. So this is how we extract that information and put it in here for you. So beta 0, the intercept term, is minus 932, which has got a p-value of roughly around 0.19. The B1 is minus 7.1, and so on and so forth. So we started with 18 observations. We used up 3 variables, so now we've got like 15 degrees of freedom. And in a null hypothesis, you might see that we have tested that all the coefficients are 0, which of course is not. So we could say that the statistically, that this model is significant. The other thing that we can do is we can actually get an ANOVA table, and we can find what could be the confidence interval for each of these three variables. And it's very, very simple. You can see that the confidence interval is for age, it's minus 15.5 and ranges from 1.32, which means that the confidence interval itself traverses the value of 0, and therefore we say that we just don't know. It's very, very wide. The weight variable, of course, is also very broad, ranging between 4.74 to 42.5. And so when we conduct the ANOVA, we see that the ANOVA is significant as well. Both age and weight are significant in terms of the analysis of variance. They are significant, although regression is not significant. But the analysis of variance then tries to figure out as to what happens to this. So a few things to note here, and you note that that both age and weight are significant in the analysis of variance. And when we start putting into the ANOVA age and weight, we see that the weight is exactly as it is in the main table, because weight was the first variable that we had put into the regression model. Then we added age. So when weight is used in the ANOVA model and then the weight is estimated, at that point the regression coefficient or the significance values are exactly very similar to the one that you get to see here. But age is not, because we have sequentially analyzed the analysis of variance. And the fact that the p-value of age does not agree with the p-value that we get to see in the main regression model tells you something. And that tells you that there is a corresponding, or there is a correlation between age and weight. Could be that as age increases, the weight kind of drops down. So young people tend to be a little heavier in this particular data set. So which is why you would like to plot the age and weight, or you'd like to run a correlation of the age and weight and see what the correlation tells us. The correlation tells us is this, that age is inversely related to weight, although it may or may not be statistically significant, but there is an inverse relationship. Now, because of this, we see that the magnitude, the point estimate of the correlation is quite high. And this might explain why this was happening, that when you put in age later on, age became quite a significant of the remainder. But when you put them in the regression equation together at the same time, age might not be a major contributor. Of course, weight was the more substantive contributor of the two. So one of the things that we would like to do now, based on our understanding of the regression model, is this, that we may omit the intercept term. So let's omit the intercept term and run it over again. Remember that when we were running this regression model and we looked at the intercept term, we stated that we could probably get rid of the intercept term because the intercept term didn't really add any additional information to us. What's a way to do that is shown in this code block. So we created another object which is now labeled as cpk.lm0, and we have stored in that object the product of the linear model, where we have regressed the creatine phosphokinase on age and weight, but we decided to take out the intercept term, so we have put a -1 onto this. One other way in which you could take out the intercept term is to put 0 and then plus age plus weight. That would do the same thing. And then we print out the summary of the CPK term. So let's take a look at the regression equations, or the regression that come out with and without the intercept. So with the intercept, you get to see that as before, age has got -7.12, the weight is 23.63, and you can see that the age is not statistically significant, but the weight is, and you can see that the adjusted R-square gives you around 40%. But see what happens when the only variables that we consider are age and weight. The age is still negative, but it has increased a little bit, the magnitude of it, and that's 9.47, but it has now attained a level of statistical significance. The weight variable, that parameter estimate has come down almost by 50%. So from 23.6 it has come down to 11.9, and you can see that this again is statistically significant. So both of them, one after adjusting for the other, has become statistically significant here. Okay. And you also see that the adjusted R-square has gone up a lot, which means that the model can now explain nearly 84% of the variability. So the intercepts explanatory power, we just don't know what sense to make of this. So then you might ask, and also take a look at the standard errors. You can see that in case of age, the standard error, or the variability, has come down, but come down a little bit, like from 3.96 to it has come down to something like 3.65. But note the standard error for weight. It has come down from 8.86 to something like 2.03. That's a huge drop, almost like a 75% drop in the standard error. You would like to question as to what does this mean? So what we get to see is this, that there is a reduction in the standard error for both age and weight, but it's much more substantial for the weight variable than for the age variable. This is because there was a correlation between the regression coefficients themselves of the intercept and the betas of the age and weight. So if we now take a look at in order to report that correlation, you report the summary of it. But then you say that, okay, I would like to have I'd like to have the correlation of the correlation coefficients, their correlations. Then you see that between the intercept and age it's minus 44, but between the intercept and weight, that is very, very high. That is almost 0.97. And then there is a correlation between the weight and the age, which we don't understand why it's not negative. But you can see that there is a relationship between weight and the intercepts, betas. That tells you that when you take out the intercept term, then immediately the standard error shrinks a lot, because now you don't really have to worry about the variability shrinks a lot, particularly more for weight variable, which are a higher correlation with the intercept. So let's take a look at the diagnostic plots, because remember, the diagnostic plots tell us quite a bit about the outliers and things like that. And you can see here that there seems to be some sort of a pattern in the residuals. So the relationship may not exactly be linear. And you can also see that the residuals are not exactly a straight line as far as a normal QQ plot. So the residuals are not really normally distributed, which was not really a surprise at this stage. And you can see that if you take the standard residuals and fitted values, you see that as the fitted values increase, there is a tendency that the residuals are also going to increase a little bit. So this is a phenomenon which is often referred to as heteroskedasticity. So it hints that a linear model probably is not the best way to explain the association between these variables and the CPK. But look at the leverage. We had discussed already the issues of leverage in, when we were discussing influencers and the outliers. And leverage is the phenomenon where an outlying variable would likely to pick up on or move the association or the fit line in one direction or the other. So if we continue with the diagnostic plot, you can see that there is an issue of the leverage that we get to see. So what we'll do is here we'll examine that a little bit more closely, and we see that the leverage itself indicates that point number 110 may be a culprit. That may be a factor which is going to distort the association between CPK and these variables. In order to better understand the leverage, we create what is known as a hat matrix. And that hat matrix is created on the basis of a phenomenon which is known as the model matrix. So when we've got a model, the model actually produces a matrix. Unfortunately, at this stage, we do not really have sufficient time, or this is beyond the scope of this particular lecture to explain in details about the model matrix. But you can use the model matrix in order to generate what is known as a predicted model matrix or a hat matrix. And that hat matrix will give us a sense of the leverage as to which point is actually becoming more and more important in understanding this. So what we do basically is we plot the leverage points, but we also plot what is known as a studentized residuals, often referred to as jackknife residuals. So what it does is it does a procedure which is known as cross-validation and resampling of the data. And by doing that, you can get a set of jackknife residuals. And here are the two things, right? You can see that both the jackknife and the studentized residuals, but more, both the jackknife as well as the leverage statistics suggest that there is one point which is like, point number 110 is the one that is responsible for for this. So if you could remove that 1, 1, 10 point, maybe we could have a different set of parameters. Lastly, of course, we are working it backwards. There is this issue around scatterplot matrix, and this is also another important point that we should note here when we are playing with R. Remember that I told you that when you start your data analysis, it's very important that you have to have a visual output of your data. This is where you do that. You plot a scatterplot matrix to get a sense of the various variables that you get to see here. So we issue the command pairs blood CPK, and in the panel that results, we say, okay, give me the smoothed data of the pairs of data that we get to see here. And you can see from here that the relationships may not exactly be a linear, can be a curvilinear relationship. So before we finish this, a couple of other points. One is this, that there are some core assumptions in multiple linear regression. In the multiple linear regression, we'd really like to find out the expected value of y. It's like a fitted value of y. And that is based on the alpha, the beta 1 of the x1 value, the beta 2 of the x2 value, and so on. You can fit as many variables as you like. So beta p times xp. The distribution of y is normal, and the expected value of y, that should be the mean, which, and the variance is constant. And the other thing is this, that the y, x1, xp, they're all multivariate, normally distributed. Like if these could be spread onto a space, that space is, you could conceptualize a three-dimensional hill for like 3 variables. That will give you sort of a normal distribution of the two variables. It is not necessary that all these things will be honored or all these assumptions will be met. But nevertheless, a multiple linear regression is a reasonable starting point to see what are the associations, or guess if we can need to make some transformations that will make it a little bit more meaningful. So to summarize, there are some strategies. You examine the distribution of each of these variables, you check for outliers and skewness, you go for a scatterplot matrix to see their distributions, and then if needed, you need to transform those variables. We'll see how we do that. And then finally, we kind of extended the concepts of a simple binary linear regression. And we learned that we can identify outliers in these things, and we can do certain things. In the next phase, we're going to look into the concepts of variable selections and model building. All right, so keep learning. Welcome back. Now that you had a sense or a way of working with the simple bits of multiple linear regression, it's just in small chunks. So you learned that you can set up a multiple linear regression equation in R. You saw that you have to follow the Wilkinson-Rogers formula of having an outcome variable and 2 continuously distributed variables. There are still a few more tasks to be accomplished. Remember that in the same as in the simple linear regression, we are still looking at outliers and influencers and some plots, and this is what we're going to explore in the next bit. Okay, so again, bring out your data sets and get rolling with us. Thanks, and let's move on to the next bit, which is multiple linear regression 2 of outliers, influencers, and other advanced